Section 16.2, Line Integrals. If f is defined on a smooth curve C given by the parametric equations x equals x of t, y equals y of t, where t goes between a and b, then the line integral of f along C is equal to the limit of the Riemann sum of f at certain sample points times delta Si, if this limit exists. The lengths delta Si are of subarcs of the curve C. So in the past, we've taken integrals, our single variable calculus integrals, over some interval from a to b. So we could have, let's say, some curve, and then we looked from a to b, and we would integrate, and we would get the area underneath that curve. So what we're doing now is, instead of integrating from some straight line segment from a to b, we're saying that we take that line segment from a to b, and we have it just curve somewhere in the plane. So we want to look at the integral over that. Notice this is not the area underneath this curve. That's not what we're doing. The thing that we're integrating is some function of x and y, which is floating above this curve somewhere. Kind of like how this function over here that we were integrating was floating above the interval from a to b. So it's the interval itself that we're allowing to be curvy. So in order to do this, we do it pretty much the same way as we would if we were doing it in single variable calculus. We chop up the interval. So when we chop up the interval, we look at each of those little pieces, and then in our case, they became rectangles. We'd stack them up. So in this case, we have to chop up our little our curve. So we chop that up, and we have to sum up all of those pieces times the value of our function. Because remember, we'd sum up a whole bunch of little delta x's, little change in x's. So now, because we're summing up pieces of some curve, we're summing up little delta s's, where s is the length of that curve. So we're summing up little arc lengths. Because we're summing up little arc lengths, though, we can come up with another formula for our line integral that doesn't rely on computing some limit of some Riemann sum. So instead, remember, the arc length can be found by integrating the square root of each of the derivatives squared if we have a parametric curve. So that means that we can replace delta Si with this square root of the derivative squared as long as we're integrating. And instead of our x and our y, we would just replace those with our functions of t, because the curve is given by parametric equations. So that means that in the end, we have everything written as a function of t. So we just have a single variable calculus integral with respect to t. So as an example, how about we evaluate this line integral of 2 plus x squared y ds, where c is the upper half of the unit circle. So remember, we're not finding the area underneath the upper half of the unit circle. We are simply using the upper half of the unit circle as our curve that we're integrating over, and this is the function that we're integrating over that curve. So I'm not actually going to draw that function, I'm just going to draw the curve. So I'm drawing this semicircle, and we just have to imagine that curve floating above there somewhere. So this is 1, this is -1, this is 0, and remember, to write out our line integral, we would have to either calculate all those delta si's, all those lengths of each of those sub-arcs, and take the limit of the Riemann sum, or we can just convert everything using our parametric equations into functions of t. If we do that, we just get the single variable calculus integral. So in order to do that, that means that we have to parametrize our circle. So this is the circle x squared plus y squared equals 1, where y is positive. So we can parametrize that by saying that it's x equals cosine t, y equals sine t, where t goes between 0 and pi. We cut it off at 180 degrees. So then our line integral over c of 2 plus x squared y ds becomes the integral from 0 to pi of 2 plus cosine squared sine t, and then we have to replace our ds with something in terms of dt, so we have to calculate the arc length. So we take the derivatives and we square them, and we take the square root. So this will be our arc length. And now everything's in terms of t. So we say this is the integral from 0 to pi of 2 plus cosine squared t sine t. And then our derivative for dx dt, it looks like it's just going to be minus sine, so we square that, we get sine squared. And then for dy dt, that'll just be cosine squared when we take the derivative and square it. So it looks like we just have ds equal to dt. That's pretty cool, because cosine squared plus sine squared is just going to be 1. So we have 2 plus cosine squared times sine just times dt. So in this case, you could have made a huge mistake and just replaced ds with dt, and it actually wouldn't have cost you anything because it turned out that this entire thing was 1. But in general, you won't be able to do that. So then I integrate, take the antiderivative, I get 2t minus cosine cubed over 3 from 0 to pi, which is just 2 pi plus 2/3. So if you wanted to visualize this, you could imagine that this is some function of two variables that's floating above this semicircle curve over here. And I don't know, maybe it's like, yeah, I can't really draw it. It's in the three-dimensional space. And what we basically got was the area that is underneath this curve, but above this semicircle. Just in this case, though, in general, the geometric interpretation of a line integral is going to depend very heavily on the context of the line integral, if there even is one. Suppose that C is a piecewise smooth curve, that is, C is a union of a finite number of smooth curves, C1, C2 through Cn, where, as illustrated in the figure, the initial point of Ci plus 1 is the terminal point of Ci, so that means the initial point of each subsequent curve is the terminal point of the curve that came before. Then we define the integral of f along C as the sum of the integrals of f along each of the smooth pieces of C. So basically just saying we chop up one big line integral over one big piecewise smooth curve into a whole bunch of smaller line integrals along the way. So let's evaluate the line integral of 2x ds over c, where c consists of the arc c1 of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment c2 from 1, 1 to 1, 2. So we will draw that. Okay, so I need to draw the parabola. So here's y equals x squared. And then I needed to stop at 1, 1. So this will be my curve C1. And here we are at the origin. And then I need to keep going to C2, which is the vertical line segment. So I'll just go up until I get to 2, 2. Or 1, 2. I didn't move in the x value, I just moved up. Okay, so that'll be C2. And as before, I need to parametrize this curve. Remember, I'm still not drawing the function I'm integrating over. I'm just drawing the function I'm integrating. I'm just drawing the curve that I'm integrating over. So I want to parametrize that. It looks like I could make x equals t, y equals t squared for our parabola. However, I don't really need to do that because I don't need another variable t if I just have x equals it and then y equals some function of that. I could just keep x equal to x and make y a function of x. That's a convenient thing we can do when we actually have our variables actually as the graph of a function already. In the previous example, we had a semicircle. So that's part of a circle, which is not a function of x or y. We'd have to solve and then have a square root plus or minus and be a mess. So we had to come up with another variable t so we could split each of them into a function. And then when we parametrized it, oh, I should have indicated this is going in that direction after you parametrize it. But you insert the t. So you insert your parameter in order to make stuff a function of something else. In this case, we already have parabola is already a function of x. So we can let x be its own parameter. We can let y be a function of that parameter, y equals x squared. And we just indicate that x goes between 0 and 1. So this would be a good parametrization for our curve C1, which goes in that direction. So that means that I can make my line integral over C1 of 2x ds equal to the integral from 0 to 1 of 2x times the arc length, which is the square root of, in this case, dx. Instead of dt, it'll be dx dx, because that's our parameter. So dx dx squared plus dy dx squared dx. So it's very convenient when you have just the graph of a function of one of the variables. You don't have to really worry about getting a t. So we have the integral from 0 to 1 of 2x times, well, dx dx is just 1. So I have the square root of 1 squared, which is 1 plus dy dx, that's 2x squared becomes 4x squared dx. And this will just be 1/4 times 2/3 times 1 plus 4x squared to the 3/2 power when we integrate. And we'll go from 0 to 1. So that's just 5 rad 5 minus 1 over 6. So what we've done so far is we've calculated this line integral, but we still have half of our curve left. So we need to parametrize that, and we need to integrate. Notice over here x is constant 1, so we can just set x equal to constant 1, and we can let y be its own parameter, because y is the only thing varying. So we just have to set y between 1 and 2. So this means that we get, let's see, the line integral over C2 of 2x ds. So that'll just be the integral from 1 to 2 of 2 times x is just 1. Then the arc length, so the square root of dx dy squared plus dy dy, because now y is our parameter. And we have everything with respect to y. So that'll be the integral from 1 to 2 of 2 dy. Because notice this derivative is 0. This one's 1, so we just have a square root of 1 squared. So that's just 2. So that means that we now have our line integral over the entire curve C as the line integrals over C1 and C2 added together. So that means that our line integral is just 5 rad 5 minus 1 over 6 plus 2. Suppose that rho of xy represents the linear density at a point xy of a thin wire shaped like a curve C. Then the mass m of the wire is given by the limit of the Riemann sum of the density times the arc length, which is just the line integral of rho ds. So the center of mass of the wire with density function rho is located at the point x bar y bar, where x bar is 1 over m times x times rho when you take the line integral, and 1 over m times y times rho when we take the line integral. So as an example, let's say we have a wire that takes the shape of the semicircle x squared plus y squared equals 1, where y is greater than or equal to 0. So similar to what we drew in example 1, and it's thicker near its base than near the top. So let's find the center of mass of the wire if the linear density at any point is proportional to its distance from the line y equals 1. Okay, let's see if I can draw this. So it's almost the same, but slightly different. So I want my semicircle, but what I want to try to do is make it a little bit wider on the bottom. So let's see. Didn't come out exactly the way I wanted it to. Let's see if I could just do it a little bit and then maybe adjust it a little more. So something like that. So notice that it's supposed to be thin at the top, but the wire gets thicker on the sides. So it gets thicker closer to 1 and -1. And we would like to do this line integral so that we can figure out what the center of mass is. So we need to parametrize it. So we'll do the same parametrization as before. We have x equals cosine t, y equals sine t, t goes between 0 and pi, and ds is equal to dt as we calculated the square root of each of those derivatives squared would add up to cosine squared plus sine squared, which is 1. So we need the density that we're going to integrate. So we have rho of xy, and they told us that it was linear density is proportional to its distance from the line y equals 1. So because it's proportional, it needs to be multiplied by some constant k. And then the distance from the line y equals 1, well, that'll just be 1 minus y. So this means that our mass will be the line integral over c of k times 1 minus y ds. And that'll be the integral from 0 to pi of k times 1 minus sine t dt. So we said y was equal to, and ds in this case was dt just because it happened to be that the arc length was 1. We can factor out our constant and take our antiderivative, and we get t plus cosine t. We evaluate from 0 to pi, and we get k times pi minus 2. So now let's get our y coordinate for our center of mass, y bar. So that'll be 1 over m times another line integral, but this time we have a y in there. And we do rho over xy ds, and we get 1 over k times pi minus 2 times the line integral of y times k times 1 minus y ds. And this is 1 over pi minus 2 times the integral from 0 to pi of sine t minus sine squared t dt, which is 1 over pi minus 2 times minus cosine t minus 1/2 t plus 1/4 sine 2t from 0 to pi. So that's just 4 minus pi over 2 times pi minus 2. Okay, so we have one coordinate. Notice the other one, though, is very easy because our curve is symmetrical around the y-axis and our function rho is symmetrical. We don't have to worry about x bar. It's just going to have to be on the line x equals 0. So we can just say that x bar will equal 0 by symmetry. Okay, so now we have the coordinates of our center of mass. It's going to be x bar y bar equal to 0, 4 minus pi over 2 times pi minus 2. There we go. and that's approximately 0.38. So if I was going to put that in our picture, it would look like over there somewhere. That's our center of mass. Next up, the integrals, line integral of f of x dy dx equal to the limit of the Riemann sum times delta xi, the change in the x value, and the line integral of f of x y dy equal to the limit of the Riemann sum times delta y, the change in the y values, are called the line integrals of f along the curve C with respect to x and y. So the original line integral ds is called line integral with respect to arc length. So this one has a nicer geometric interpretation in terms of cutting up the curve that we're integrating over into little pieces and adding up the lengths of each of those pieces. These values don't have as clear of a geometric interpretation. What you're doing is you're cutting up a change in x value and cutting up a change in y value. So it kind of, it's like a hybrid or like a halfway between each of those integrals. You can't really draw what's going on as easily or even imagine what's going on as easily. But it turns out that these definitions are actually useful and they actually will come in handy very soon, even though we can't even imagine why we'd want these just half of a change, you know? So the line integrals with respect to x and y can also be evaluated by expressing everything in terms of t, as we saw before. Notice that if you have x equals to x of t, some function of t, then if you want dx, then by the chain rule, it's just going to be x prime of t times the derivative of what's inside dt. So that means that dx gets replaced with x prime of t dt, dy gets replaced with y prime of t dt, and we can integrate everything with respect to t. So when line integrals with respect to x and y occur together, we have this shorthand that we use. So remember, when you have an integral added to another integral, if they're both with respect to the same thing, then in general you would just add them together and do one big integral because of the linearity property of integrals. Because they have different things that we're integrating with respect to, usually we would not add these together, we'd keep them separate. But because it's going to happen so often, we're just going to write one integral to save space. So what we'll do is we'll remember that they're separate integrals, but we'll write them together by just throwing one integral sign and just keeping the dx with the x terms and keeping the dy with the dy terms. So how about we evaluate the line integral over c of y squared dx plus the line integral over c of x dy, where c equals c1 is a line segment from -5, -3 to 0, 2. So we'll do this line integral first. So as before, the first thing that we have to do whenever doing a line integral is express everything in terms of t, so we have to parametrize it. So we have to come up with a parametrization of the line segment. Remember that in section 12.5 we did this though. We said that we could parametrize a line segment r of t if we set that equal to 1 minus t times our position vector for our initial point, r0, plus t times our terminal position vector r1, where t goes between 0 and 1. And in this case, we have our initial point equal to -5, -3. So that becomes our initial vector, and we have r1 equal to 0, 2, so that becomes our terminal vector. So if we were to plug these in for r0 and r1, and then we combine everything together so that we have just one x component, one y component, then we'll see that x is equal to 5t minus 5, and y is equal to 5t minus 3, where t goes between 0 and 1. So this means that dx is 5 dt, and dy is 5 dt also. So this means that our line integral for C1 of y squared dx plus x dy is just the integral from 0 to 1 of 5t minus 3 squared times 5 dt instead of dx plus 5t minus 5 times 5 dt instead of y. So this is just 5 times the integral from 0 to 1 of 25t squared minus 25t plus 4, because now that we have one integral, everything in terms of t, we can just combine our integrals using linearity and just have everything with just respect to t, dt. So this is just 5 times the integral, 5 times the antiderivative, which is 25t cubed over 3 minus 25t squared over 2 plus 4t from 0 to 1. And that's minus 5, 6. So now let's check out the second part of our line integral. We're going to do it over C2 now. So we need to parametrize the parabola. Notice it's an x equals parabola, so everything's already in terms of a function of y. So we might as well just make the y the parameter. So how about we make x equal to 4 minus y squared. We'll let y stay y, and we'll integrate from minus 3 to 2. So notice dx is just minus 2y dy, and we'll end up with the integral over C2 of y squared dx plus x dy becoming the integral from minus 3 to 2 of y squared times minus 2y dy plus 4 minus y squared dy, which is the integral from minus 3 to 2 of minus 2y cubed minus y squared plus 4 dy, which is minus y to the fourth over 2 minus y cubed over 3 plus 4y from minus 3 to 2. And that's just 40 and 5/6. Well, as we've seen many times now, there's nothing special about 2 dimensions. We'll just add another variable and define the line integral on 3-dimensional space as the limit of the Riemann sum of f of x I star yi star zi star delta si, provided the limit exists. And that means that we have almost the same arc length formula. We just add the dz dt squared with respect to t. So because this is becoming such a mess, we would now like to write it more compactly. So we can use vector notation to say that this is just f of r of t. Well, r of t is the parametrization of our curve, and this square root of each of the derivatives squared is, notice, just the length of the derivative, because that's how we get the magnitude of a vector. We take the square root of each of the components squared. So this provides a much shorter way of writing our line integral. Notice that in the special case that our function that we're integrating is 1, then we're integrating just 1 ds. So that means that we're getting the arc length. We literally just get the arc length formula. As before, we can define the separated line integrals with respect to x, y, and now z. And we do that just by writing each of our sums with a delta xi, delta y, delta zi. So when we convert it to the integral, we get dx is x prime of t dt, dy is y prime of t dt, and dz is z prime of t dt. As with line integrals in the plane, we evaluate line integrals of the form some function of x times dx, some function of y dy, well, some function of x, y, z, x, y, z, all of them. There could be y's over here even when we integrate with respect to x, just like we had in the previous example, and some function of x, y, z, dz. We do all this together, even though we have these different differentials, because we just like to save space, we just write one integral, even though it's three separate integrals. And we express everything in terms of the parameter t, so that in the end, we just have one single variable calculus integral. If we're not using t, sometimes we'll express everything in terms of y or in terms of x, if it's a function of that particular variable. So now we can integrate over space curves for line integrals, so let's do that, where c is the circular helix. So we'll say that the line integral over c of y times sine z ds is equal to the integral from 0 to pi. Notice I didn't have to come up with parametrization because they gave it to me, even though we have done this parametrization ourselves before. So I'll just plug in sine t for y, and for z is equal to t, so sine of z is just also sine of t. And then I have the square root, a little bit messy, of dx dt squared plus dy dt squared plus dz dt squared. And we're doing this all with respect to t, so dt. So then we'll get the integral from 0 to 2 pi of sine squared. And in the square root, notice we have derivative of x is minus sine squared is just sine squared. Then we have cosine squared for the derivative of y squared. And then taking this derivative, we just get 1. So that's 1 squared is 1. So that means that this entire thing becomes square root of 2 because this is 1. So I'll just pull out the square root of 2. And left I have the integral from 0 to 2 pi of 1/2 1 minus cosine 2t using my half angle formula. That's how we evaluate our trig function squared, and we get square root of 2 over 2 times t minus half sine 2t from 0 to 2 pi, which is just square root of 2 times pi. Let's do an example where we have to come up with the parametrization ourselves. So they gave us a line integral, they gave us c consisting of line segment c1 followed by line segment c2. So we'll try drawing the curve that we're integrating over in the xyz space. So we'll start at 2, 0, 0, and then we go kind of like that until we get to 3, 4, 5. So I'll write that 2, 0, 0, and then 3, 4, 5. So this is C1. Then we will go down until we get to the point 3, 4, 0. Okay, in the xy plane. Alright, so this will be C2. So how about we parametrize C1? So for C1, we'll use our parametrization of a line segment. R of t is 1 minus t times our initial vector, which in this case is 2, 0, 0, plus t times our terminal 1, 3, 4, 5, and multiplying through and then Combining everything, we get that our x component is 2 plus t, our y is 4t, and our z is 5t. So that means that we can write x equals 2 plus t, y equals 4t, and z equals 5t, where t goes between 0 and 1. So this is for C1. Now we parametrized it. So now we'll get our line integral over C1 of y dx plus z dy. Notice I can have y's over here, even though it's a dx, because I'm going to convert everything to t anyway, plus x dz. And that'll be the integral from 0 to 1 of 4t for y. Then notice dx is just dt, because the 2 is a constant. I'll add that to, let's see, z is 5t. But then I need to take dy. Notice dy is 4 dt. So multiply by 4 dt. Last but not least, we have 2 plus t for x. And then we need dz, which is 5 dt. Okay, so we take our integral, simplify a little bit, we get the integral of 10 plus 29t dt. And that's the antiderivative, so it's 10t plus 29 times t squared over 2 from 0 to 1, which is just 24.5. So now let's get our line integral over C2, so I need to parametrize C2. So again, we'll use our line segment parametrization, so it's 1 minus t times 3, 4, 5 plus t times 3, 4, 0. And that'll just become 3, 4, 5 minus 5t. So x is 3, y is 4, z is 5 minus 5t, and t still goes between 0 and 1. So now we parametrize this guy. So we can write our line integral now. Oh, well, by the way, notice dx is 0 and dy is 0, because these are constants. So 2/3 of our line integral is about to disappear. So line integral of y dx plus z dy plus x dz is just going to be the line integral of x dz. So that's the integral from 0 to 1 of 3 for x times minus 5 dt for dz, and that's just negative 15. Wonderful, so we get the line integral over C in general of y dx plus z dy plus x dz is equal to 24.5 minus 15, which is 9.5. And by the way, notice it makes sense that these guys would be 0 because look, we're just going straight down over here. There's no change in x or y. Remember that in the past we've defined work to be force dotted with displacement. So we're going to basically do that by taking the force times displacement over an entire curve as the dot product summed up over each of those pieces of the curve. So we look at each of these little pieces, we take our dot product force and displacement, and we end up with a Riemann sum. So we take the limit of that and we get a line integral because we're doing this all with respect to arc length. So notice when we take a dot product, we get a scalar. So this is perfectly valid for us to take a dot product and then do an integral over it. So if the curve C is given by the vector equation r of t equals x of ti plus y tj plus ctk, then remember our unit tangent vector is r prime over its length. So that means that we can rewrite the work as the integral of the dot product of f dotted with t, but we replace t with r prime over the length of r prime. Remember that ds was arc length. We abbreviated, well, not necessarily abbreviated, we had a more concise notation by writing r prime of t dt, the length of r prime of t dt, because that was what arc length was. So notice that it'll just cancel. So we can rewrite our work done as the dot product of f of r of t with r prime. And in order to try to abbreviate this, we write f dot dr. So this wouldn't really make sense otherwise. We're basically saying that when we put a dot product in for a differential, what it means is this, really. It's just shorthand. So if f is a continuous vector field defined in a smooth curve C, given by a vector function r of t, where t goes between a and b, then the line integral of f along C is f dot dr, which we just said is an abbreviation for f of r of t dot r prime of t dt, which in turn is f dotted with t ds. As we said, it's the work done. Notice it makes sense that you'd want the unit tangent to dot with your force, because that's literally how much you're being displaced along the curve for each of those little pieces. So let's find the work done by the force field f of xy equals x squared I minus xyj in moving a particle along the quarter circle r of t equals cosine ti plus sine tj, where t goes between 0 and pi over 2. So as before, we need to write out our parametrization. So x equals cosine t, y equals sine t. We'll use our parametrization, though, to evaluate f of r of t, because it'll be easier to take our dot product than to have to worry about calculating the unit tangent. We could just take the derivative. So if we take f, we plug in our parametrization r of t. We're plugging in for x cosine. So we get cosine squared ti minus x times y is cosine t, sine t. That'll be for j. And that's f of r of t. We also need to dot it with r prime, so let's calculate that too. So we'll get r prime is equal to minus sine t I plus cosine tj. We take our derivative. Okay, I think we're ready to do our line integral now, because we could take our dot product. So we'll get that f dotted with dr is equal to the integral from 0 to pi over 2 of f of r of t dotted with r prime, and that's just the integral from 0 to pi over 2 of, let's see, we're going to take cosine squared dotted with minus sine, and then we'll take cosine sine dotted with cosine. So we'll end up with a cosine squared and a sine squared in both. Well, we'll end up with cosine squared and a sine in both. So it looks like we have minus sine cosine squared and minus sine cosine squared. So that's minus 2 cosine squared sine. So we take our antiderivative, which is convenient with the nice little substitution because we have sine right next to cosine squared, and we'll end up with 2 times cosine cubed over 3 from 0 to pi over 2, which is negative 2/3. So let's see if I can sort of draw what's going on here. It's going to be very rough because it's pretty hard to visualize work being done, at least for me. So I have my semicircular curve that we're integrating over. Well, not semicircle, it's quarter circle. So, and it's parametrized this way. And then let's see if I can draw my force field. So let's see. It goes something like this. Roughly that. Notice that the work done is negative because the field is kind of pushing back on the curve in the direction that the curve is traveling. So the work done is, the movement along the curve is being impeded by our force field. So our work has to be negative. How about we evaluate this line integral now for our force field F? So again, we need to look at our parametrized curve R of t. So in that case, it's going to be t for the ith component, t squared for j, and t cubed for k. And we need our derivative, which we'll dot with f of r. So for our derivative, it's just 1i, because derivative t, and then 2t for j, and then 3t squared for k. So now we need f of r of t, which we're going to plug in for our dot product. So that'll be t cubed I plus t to the 5th j plus t to the 4th k. All I've done here is just plug in t for x and then t squared for y. That's how I get t cubed, and then plug in t squared for y and then t cubed for z, etc. So then my line integral over c of f dot dr is equal to the integral from 0 to 1 of f of r of t dotted with r prime of t, and that's just the integral from 0 to 1 of t cubed plus 5t to the 6th dt, which is t to the 4th over 4 plus 5t to the 7th over 7 from 0 to 1, and that's 27 over 28. Last but not least, we unite our two different definitions. It turns out that the work done, f dot dr, is exactly equal to the line integral of p dx, line integral of q dy, line integral of r dz, which we abbreviated by the line integral of all of these guys added together, which is, I guess, our real motivation for wanting to split up our line integral to begin with. And proving this is actually surprisingly easy. It just follows straight from the definition of the dot product. So f of r of t is just pi plus qj plus rk. And then r prime of t is x prime, y prime, and z prime. So when we dot those together, we end up with p of x of t times x prime, well, p of x of t, y of t, z of t times x prime, which is a pretty long mess, so that's why we just write p usually. And then x prime of t dt just becomes dx. And similarly, we take q, we write it as x of t, y of t, z of t, parametrize it, times y prime of t dt, which is just dy when we go back through and like deparametrize. And the same thing for r and z prime.